Hello and welcome to a new video of my Let's Code series. My name is Ishin, and in this new series I want to actually code some Advent of Code puzzles. Yeah, instead of the usual video game series I was doing up until now. But to be honest, I'm out of ideas, and yeah, I haven't done the most recent Advent of Code challenges yet, 2022. To be entirely honest, I have only done the challenges up till 2019, and then I just had so much on my plate that I didn't get around doing the puzzles. But now, I guess, yeah, you could say I'm in a bit of a slump right now. I wanted to code my own video game, and currently this is not progressing very well, and somehow I lost all the motivation to do anything on that. So here I am making this video and doing the 2022 challenge, I guess. So yeah, if you're interested, just subscribe and you'll see more of this. I plan to do all the 25 puzzles. Let's start with day one, shall we? Yeah, these puzzles always come with like sort of background story of Santa and how he's gonna deliver presents on Christmas. But let's just jump right into it. I think the introduction goes up till this point. The jungle is too overgrown and difficult to navigate in vehicles or access from the air. The elves' expedition traditionally goes on foot. As your boats approach land, the elves begin taking inventory of their supplies. One important consideration is food. In particular, the number of calories each elf is carrying. The elves take turns writing down the number of calories contained by the various meals, snacks, rations, etc. that they've brought with them, one item per line. Each elf separates their own inventory from the previous elf's inventory, if any, by a blank line. For example, okay, we have this list here, and there's always a blank line in between the numbers. And this is probably the first elf, that's the second elf, that's the third elf. And each line corresponds to a food item with a certain amount of calories. In case the elves get hungry and need extra snacks, they need to know which elf to ask. They'd like to know how many calories are being carried by the elf carrying the most calories. In the example above, this is 24,000 carried by the fourth elf. Yeah, 7,000 plus 8,000 plus 9,000 would be 24. Right? Yeah. 24,000. Find the elf carrying the most calories. How many total calories is that elf carrying? And we have our puzzle input here. Great. Okay, this seems to be very straightforward. I don't even think I need a whole video for that. Maybe we can do day 2 as well in this video. I don't know. So first of all, let's create our new project library. Name it AOC 2022. Okay, let's remove all of this, and then I'm thinking of having one file per day. So let's name this day 1, and then we need to register it in our library file. Okay, and then let's also download our puzzle input. day1.text. Okay. In my opinion, there are like two kind of modes on how to approach Advent of Code puzzles. So the first mode would be like competitive mode, I would call it, which means you want to solve the puzzles as fast as possible to land you a spot on the leaderboard. That's what I'd call the competitive mode. And of course, in that mode, you would have to do it as fast as possible. Maybe like skimp in terms of performance or code clarity, I would say. And I don't think we need to be operating in this kind of mode right here, because first of all, it's not December. Second of all, it's, we cannot land on the leaderboard anyway anymore. So we will be operating in the other mode, namely the non-competitive mode. So my approach to these puzzles is I have a first step of parsing the input. And then in the second step, we'll actually solve the puzzle. So if you're in competitive mode, you probably want to skip the parsing the input correctly part. You would probably parse it, but then evaluate directly on what you want to know. That will save some time. But my approach is to always have like a struct or like a state that corresponds to the puzzle input as like a starting point, and then we operate on that state to get to the solution. That said, the kind of struct I'm envisioning for this kind of puzzle input would be a list of elves, and each elf has a list of food items. So let's do that. So first of all, let's get our input. Actually, let's make this static, which would be a string slice, and then we just include the string from our file. And we have to, of course, make it uppercase. Yes. All right. And then we'll just create a function called part1 and part2. As you, like, just for your information, there's, for each day, there are 2 parts of the puzzle. So the first question is, how many total calories is that elf carrying? And then when we get the answer submitted, we get another question, so to say, which we need to solve. That's how this works. And let's just make this part 1 a test so we can directly execute the function inside VS Code and get to our answer. Yeah, let's first create our struct for storing the input state. Let's say we need to have a struct called elf, I guess, and then we have food items, which is like a vector of calories. So usize. Yeah, or let's make it, let's make it u64, I guess. Doesn't really matter. Okay, and when we parse it, let's call it parse input. And then we want the input as an argument, which is a string slice, and then we will return a vector of elves. So this is pretty straightforward. We just need to split the string using the 2 new lines. Yeah. Hold on. Let me make it LF, line feed only, so we don't have any problems parsing this. Okay, let's just say we want to split it up. Split it using this pattern here, 2 new lines, 2 consecutive new line characters. And then we will map. This is now a string slice. I don't know. Let's call it calories. I don't know. And then we just need to split the calories at new lines, or we could just use lines for that, yes. And then map it to have a line. And we need to parse the line into a U64. And this will return a result type. So since I don't want to really deal with result types, let's convert it into an option. And instead of map, let's use filter map. So if the parsing did not work, then we just ignore it completely, so to say. And this would be, we can collect this into a list, into a vec. And actually we can directly create elf right here. Food items would be that. And then we collect this into a list. I don't think I need this type information here. Rust is able to figure that out by itself. Okay, so parse input will simply create a list of elves. And let's try it right away. Let elves equals parse input. And then let's print it out to see if we did everything correctly. Elf does not implement debug. Yes, let's implement derived debug. Let's run this. And yeah, looks like it's going well. And we also need to figure out the sum of all items they are carrying, right? So let's introduce a new function. Let's call this calories. Or some calories, something like that. And then we just need to get to food items and turn it into an iterator, then sum it up. And that should be it. Very straightforward. And now we need to find the elf with the most calories. So elves dot. Okay, that's a little bit tricky, I suppose. Let's iter over elves, and then there is a max function, max by. We would need max by key, I think. Max by key takes a function which has the item as an argument, and we would need to return something that implements ORed. Yes. So elf, we just need to elf call some calories, get the sum. And this will return an option of an elf. Actually, I don't even need to get the elf itself. We just need to get the sum, so we can simply map it. Get the sum. And then we have a list, an iterator over all the calorie sums. And then we just call max. And that's it. Let's unwrap it as well. So we do not need to care about the option. Here we go. We don't need to debug print this either. So the answer is 74,394. Let's see if this is correct. Yay, we got 1 star. And now to part 2. By the time you calculate the answer to the elf's question, they've already realized that the elf carrying the most calories of food might eventually run out of snacks. To avoid this unacceptable situation, the elves would instead like to know the total calories carried by the top 3 elves carrying the most calories. That way, even if one of those elves run out of snacks, they still have 2 backups. In the example above, the top 3 elves are the 4th elf with 24,000 calories, then the 3rd elf with 11,000 calories, then the 5th elf with 10,000 calories. The sum of the calories carried by these 3 elves is 45,000. Find the top 3 elves carrying the most calories. How many calories are those elves carrying in total? Okay. I don't get this premise. The elves would instead like to know the total calories carried by the top 3 elves. Okay, why do they need to do that? Even if one of those elves run out of snacks, they still have 2 backups. I mean, this is still unsustainable, right? What if all the 3 elves are out of food items, right? Then they need to calculate it again, right? So why not just do that? Calculate again every time. Oh, so during the calculation, maybe some other elf already ate everything the top elf already had. Okay, that makes sense, I guess. Yeah. Okay, let's add a function called part 2. As usual, we need to pass the input, and then yeah, how about we just sort the array, right? Sort the vec. Sort by cached key. Elf.sum calories. That should do it. Then the first 3 are actually the elf with the least amount of calories. So we need to reverse it as well. Then we just need to iter over it, and then take 3, the first 3, and then map to the calories, and then sum it up. That should do it. Now I just need to print this and we're done, theoretically. Okay, 212,836. Yay! Okay, we got our first day 2 stars. And that was only 11 minutes. Yeah, this does not fill a whole video, so I'm just gonna go on with the second day. Okay, let's go. Let me prepare everything. Commit this. Day 1. 2022, day 1. Sure. Let's do our second day. Okay, the elves begin to set up camp on the beach to decide whose tent gets to be closest to the snack storage. A giant rock, paper, scissors tournament is already in progress. Rock, paper, scissors is a game between 2 players. Each game contains many rounds. In each round, the players each simultaneously choose one of rock, paper, or scissors using the hand shape. Then a winner for that round is selected. Rock defeats scissors, scissors defeats paper, and paper defeats rock. If both players choose the same shape, the round instead ends in a draw. Appreciative of your help yesterday, one elf gives you an encrypted strategy guide, my puzzle input, that they say will be sure to help you win. The first column is what your opponent is going to play A for rock, B for paper, and C for scissors, the second column. Suddenly, the elf is called away to help with someone's tent. Sounds like a scam, actually. A strategy guide? If someone knows the strategy guide, they can completely, dominate me. Okay, whatever. The second column, you reason, must be what you should play in response. X for rock, Y for paper, and Z for scissors. Winning every time would be suspicious, so the responses must have been carefully chosen. The winner of the whole tournament is the player with the highest score. Your total score is the sum of your scores for each round. The score for a single round is the score for the shape you selected. 1 for rock, 2 for paper, 3 for scissors, plus the score for the outcome of the round. 0 if you lost, 3 if it was a draw, and 6 if you won. Since you can't be sure if the elf is trying to help you or trick you, you should calculate the score you would get if you were to follow the strategy guide. For example, suppose you were given the following strategy guide. This strategy guide predicts and recommends the following. In the first round, your opponent would choose rock, and you should choose paper. This ends in a win for you with a score of 8. 2 because you chose paper and 6 because you won. Okay. In the second round, your opponent will choose paper and you should choose rock. This ends in a loss for you with a score of 1. The third round is a draw. In this example, if you were to follow the strategy guide, you would get a total score of 15. Okay, this is a little bit more convoluted. So we need to parse this input correctly. That's fine. Let's copy the same code for our input, day 2, and write our parser. Parse input with the input as argument. So I think we need an enum called a, choice. Let's call it choice. We have rock, paper, and scissors. And our strategy, our strategy is actually just a list of choices, like a tuple of choices, choice. The first one is what our opponent will do, and the second one is what we are going to do, right? The first column is what my opponent is going to play, and the second column, or at least that's what I'm thinking, is what we should play in response. Well, not in response, because we're playing simultaneously, but I get what they meant. Okay, so as before, we can get the lines and then map it. It's actually 3 characters each line, or 4. But let's split as well. Split white space. What does that do? It will give me an iterator of string slices. Let's call it tokens. And then we have opponent token, which is the first token. Let's make it mod. And we have my own token, which would be the second token. And these are options, right? Let's make it a filter map so we ignore all the input or all the lines that are invalid. This will of course return a strategy, and let's match on opponent token, player token. So first of all, let's implement some conversion traits. Implement from string for choice. Error, I don't know. Let's make it an empty tuple. If s equals a, then or s equals x, I guess, then return okay, choice, rock. Was it rock? A is for rock. Rock, paper, scissors. Exactly. Okay. Otherwise, return an error. Else if s equals b or s equals y, return paper. Else if s equals c or s equals z, return scissors. And else return the error variant. Oh yeah. Yeah, I completely forgot that we can omit the parentheses in if statements. Yep. Much better. Okay. Now let's just match opponent and player token. If it's a sum for both, then we can say we can return a sum of opponent token dot parse choice, parse into choice, player token parse to choice, else we will return none. And now we are returning a tuple. Yeah, we need to match this again, I think. Let's match on the parse thing again. And only if both are okay, opponent choice, player choice, we will return sum with opponent choice and player choice. Otherwise, we will also return none. That should be okay. And then we will be collecting it into a vec. Let's test it out by adding a part1 function. Let input equals parse input, and print out the input. And as always, we need to derive debug for this. Okay, looks good. So now what do we do? There are scores. There are rounds. A score is given for the shape I selected. 1 for rock, 2 for paper, 3 for scissors. Okay, let's implement this first. Let's add a score function on choice, which is let's make it U64. Okay, let's match self. Rock, we will have 1, otherwise we have 2 and then 3, right? Two for paper, 3 for scissors, okay. And we need an outcome. I think we need also to derive partial equality and equality on this. And we would need another function determining the logic of rock, paper, scissors. Let's call this wins against. And then we have another choice and it will return a boolean. No, this is bad because there are 3 states, right? Either we win, either we lose, or it's a draw. So let's just create a new enum. Let's call this outcome. Win, loss, draw. Let's call this fight and we will return an outcome instead. And yeah, that would be the opponent's choice. Let's match self and opponent. So first of all, if self equals opponent, then we will return outcome draw. So we will have this case covered, this case covered, and this case covered. Yeah, we make this a borrow instead. Everything else is unreachable. Actually, we can just remove this thing and everything else would be a draw. And then we have, so need to do some thinking. If we have rock and our opponent has paper, then it's a loss. Conversely, if we have paper, the opponent has rock, we will have a win. If we have rock and the opponent has scissors, then we will win. Conversely, if they have scissors, we have rock, we will lose. If we have paper, they have scissors, we will lose. And conversely, we will win. Is that alright? I don't want to double check this, so it has to be. And then we will also add a score function for the outcome. Okay. Let's move this somewhere else. Impl outcome, let's call, let's have a score function. Match self, and then if it's a win, we will get 6 points. Was that so? 6, 3, and 0. If it was a draw, we'll get 3. If it's a loss, we'll get 0. All right. Wonderful. And what do we want to know? What would your total score be if everything goes exactly according to your strategy guide? Okay, assuming the predictions are correct and assuming I follow the strategy guide to the letter, I would need to iter over all our inputs. Iter. And then map, we will have 2 choices, namely the first one is the opponent choice and then second one is player choice. And we would then calculate player choice dot fight opponent choice. and get the score and add to the score of our choice, right? Okay, it's a little bit weird, but okay, why not? Sure. And then we just need to sum everything up, right? So this should be our score. And we will sum U64. All right. 9,241 is my score. Not sure if it's high or low. Yay! Part 2. The elf finishes helping with the tent and sneaks back over to you. Anyway, the second column says how the round needs to end. X means you need to lose, Y means you need to end the round in a draw, and Z means you need to win. Good luck! The total score is still calculated in the same way, but now you need to figure out what shape to choose so the round ends as indicated. Okay. So actually, Z, Y, X do not represent our choice. They represent the outcome. So let's implement from string for outcome. Error would be empty tuple because I do not have any error information. And yeah, if s equals x, then it should be what again? A win? X, no, I need to lose. Okay, so we want to lose. Else if s equals y, we want to draw. Yeah, and z means we need to win. And else it's an error. Loss. Okay, let's call this... No, we have a bit of a problem here with our naming scheme. Yeah. Let's remove strategy again. And call this parse input 1. Part 1. Parse input part 1. And we will have parse input part 2, which will give us a vec of tuples, namely choice and the desired outcome. Okay, so we will keep all this code, but instead of parsing it into a choice, we will call this outcome token. And pass this into an outcome. And yeah, that should do it. Let's create a new test case for part 2. Let input equals parse input part 2 of our input. And what do we need to know? We will still want to calculate the total score, but now we need to figure out which choice to make if we want to have the desired outcome. For that, let's add a new function called I don't know what to call it. Let's make it a static function called from outcome. So our API would look like choice from outcome, and we will supply an outcome and our opponent's choice, and this will construct our choice. If outcome equals outcome draw, and for that we need to derive something, derive equality, then we will return opponent choice.clone, and we would need to derive clone on choice. And now, otherwise we need to match outcome with opponent choice. Actually, as before, we instead of an early return, we could just do this. Okay. So if we want to win and my opponent has rock, we would need paper. And we would need scissors for that and rock for this. I'm sure there's an easier way to do all of this. Okay, that should be it. I'm sure there's an easier way to model all of this, right? If we use modular arithmetic with n equals 3, then we have 0, 1, 2. If 0 is rock, 1 is paper, scissors is 2, then you have to figure out which one rock should beat. We just need to subtract 1, right? So 0 minus 1 would be minus 1, so equals to 2, which would be scissors. Yeah, I feel like using modular arithmetic, we can avoid all of this, actually. The problem is, I don't think I can do arithmetic on enums, can I? Not sure. Self plus 1, that doesn't work, right? Does it? Cannot add integer. How about SU64 and then plus 1? Casting just derive copy. I don't care. Okay, I can cast self as an integer and then plus 1. It is possible. Okay, then yeah, then to figure out what outcome is there, we just need to figure out we just need to use modular arithmetic, right? If self equals opponent choice, then it's a draw. Else if self plus 1 or SU64 plus 1 modulo 3 equals opponent choice SU64. I'm not even sure why it has to be U64. Let's make it U8. Let's dereference this. We need to dereference everything. Outcome draw, okay. So if +1 equals opponent choice, so if I have rock and my opponent has paper, or if I have paper and my opponent has scissors, or if I have scissors and my opponent has rock, then it's a loss for me. Else if self is u8 minus 1 modulo 3, or actually to avoid negative numbers, let's +2 modulo 3 equals opponent choice as u8, then it's a win for us. Okay, this makes it much more elegant. We're missing an else clause, so let's make the draw an else clause. Yeah, much better. Okay, and what about this? From outcome. We just need to match outcome. If it's a win, if it's a draw, we would need to add 0, right? If we want to win, then we need to... If we need to win, then we need to add 1, right? So if my opponent has rock and I need to win, then I would add 1 to it, paper. I need to have paper. Otherwise, I would need to add 2, scissors. Or add -1 in that case. Yes, let's call this offset. And what we need to do is adding the offset to our opponent choice. And since choice is now copy, let's just forget about the borrows. So opponent choice as u8 plus offset would be my choice as choice. Does that work? No, doesn't. Okay, let's Google. Is this even possible? Okay, there's actually no safe way to do this, so let's forget about everything and just match on this, I suppose. Oh yeah, we forgot the modular arithmetic. We need to modulo 3 all of this. Okay, if it is 0, then it's choice rock. If it's a 1, it's paper. If it's a 2, it's scissors. And otherwise it's unreachable because 3 is our base. Okay, that should do it. So let's run part 1 again to see if that's still the same number, 9,241. It is, so everything's fine. Okay, now what are we doing? Now our strategy is a list of 2 poles, choice and outcome. And we would also need to iter over our strategy. We have our opponent choice, but now we have the desired outcome on the second place. And then we would need to figure our choice based on the desired outcome from outcome. Outcome is the desired outcome, and opponent choice is opponent choice. Sure. And then let's copy everything so we don't have the borrows anymore. And we do the same math as before, player choice. Find opponent choice.score. Actually, we don't. We can just use desired outcome.score plus player choice.score. No method map on type copied. That's interesting. Do we not derive copy for outcome? No, let's do it. Here we go. That should be it, right? Let's make it look a little bit nicer, the arguments on our functions, because now that choice is copy, we can remove the borrows from everywhere, actually. Yeah, we don't even need to borrow the self in these functions anymore, but I just keep it. This can be also copied. So running part 1 again, 9,241, run part 2, and it's 14,610. Let's see if this is the correct answer. Yes, it is! So I have the first 2 days of Advent of Code done, and we have 23 more days to go. If you're interested in this series, click on like and subscribe. Write down in the comments which day you found most interesting. If you've played Advent of Code 2022, let me know which puzzle you found most interesting. That said, thanks for watching and see you soon. Bye!